In this fourth video on Chapter 12, Functions of Several Variables, we're going to talk about how to find maxima and minima when we have a function of two variables. Let's start with our function z equaling f of xy, and let's discuss the approach that we need to take to find max and min. So first, what we need to do is set f sub x, the partial with respect to x of f equal to 0, and set f sub y, the partial with respect to y of the function z equal to 0. We're going to then find what we call critical values, same as in Calculus 1. Next, we have to calculate what we call the discriminant d. The discriminant is defined as discriminant at a point AB, which would be a critical value, is defined as the second partial with respect to x times the second partial with respect to y minus the mixed partial f sub xy squared. And we have enough then to determine if we have a max or a min if f sub xx at our critical value AB is less than 0 and the discriminant is positive. So second derivative here is negative. It's not exactly like exactly concave down because it's in 3 dimensions, but if you think of it this way, it's concave down, and that implies that we have a maximum if we have f sub xx at our critical value AB is greater than 0, and the discriminant is still positive. We have a relative minimum, and then the final check would be, let's call this A, B, and then C. If the discriminant is negative, we have a saddle point. So when the discriminant is less than 0, we have a saddle point, and if the discriminant is equal to 0, our test is inconclusive. So let's look at a couple of examples of how we find max and min for functions of two variables on the next blackboard. So the function we're working with, f of xy, is 1/2 x squared minus xy. We're going to find f sub x, partial with respect to x, and that's going to be 2. That's going to be x minus y, and we are setting this equal to 0, so that implies that x equals y. We're going to take f sub y now and set it equal to 0, so f sub y would be simply minus x, and setting that equal to 0 implies that x equals 0. So since x equals y, our critical value is going to be x equals 0, y equals 0, or the point 0, 0. Now let's calculate what we need to find the discriminant. F sub xx is going to be 1, f sub yy is going to be the partial minus x with respect to y, which is 0, and the mixed partial f sub xy is going to be minus 1, and the discriminant is f sub xx times f sub yy minus f sub xy squared, so it is 1 times 0 minus 1 squared, which is less than 0, so therefore at the point 0, 0 we have a saddle point. So these kinds of points are called saddle points because they actually look like a saddle. The surface looks like a saddle. Let's show a plot of this function on the next blackboard. So here on this blackboard we have a rough sketch of this function f of x y equals 1/2 x squared minus xy. And you can see that if you move in this direction here, and so you trace out the graph like this, that you wind up having a relative maximum point with respect to this arc right here. However, if you trace out the graph along this direction, moving toward you out of the plane of the blackboard, so along this, you see that you have a minimum, and so you actually create a saddle, and that's why it's called a saddle point, right there. On the next blackboard, we're going to look at another function of x and y and find out whether it has maxes and mins. So here's our function. Let's calculate f sub x. That would be 3x squared coming from this term, and a minus 1 coming from this term. Partial with respect to x of all of these three terms is 0. And then in calculating f sub y, that partial is coming from those two terms, so it is 3y squared minus 6, and the partial coming from these three terms is 0. So we're going to set both of these partials equal to 0 and find out what critical values we get. So this first one yields x is plus or minus, and so x solutions are plus or minus square root of 3 over 3, and y solutions are plus or minus square root of 2. So we have 4 critical values. They are plus or minus square root of 3 over 3, comma, plus or minus square root of 2. So let's check them out to find out what kind of critical values they are. So we calculate f sub x, and that is 6x. We calculate f sub y, and that is 6y. And we calculate the mixed partial f sub xy, and that is 0. So the discriminant is f sub xx times f sub yy minus f sub xy squared. And so as we have rewritten the critical values separately here, so if we check out each critical value by plugging into the discriminant, noting that f sub xx is this and f sub yy is this. So here, with both x and y coordinates being negative, the product f sub xx, f sub yy is going to be a positive number. Here with the x value negative, the y positive, f sub xx times f sub yy is going to be a negative number again here, positive number again here. So looking back to our requirement, for us to have a max or a min, the discriminant has to be positive, and when the discriminant is negative, we have a saddle point. So if we go back to where we were, we see that we have saddle points here and here, and with the second derivative negative here, we're going to have a relative max, and with the second derivative positive here, we're going to have a min. So recapping, we had a max here, a min here, and then a saddle point here and here. In this next example, we're going to look at how to find a volume integral. In this case, it'll be the volume under a surface. So the function that we are working with is this function, z equals f of xy equals 1 minus x squared minus y squared. This is a relatively easy function to graph in 3D, so let's do that. In the zx plane, this plane right here, the 1 minus x squared part of the function is what we are looking at, and we're going to have y equals 0 there. So what we've got is this parabola opening downward. And then in the zy plane, this plane right here, we've got the same thing. We've got a parabola opening downward in that plane, in this plane. So if we pair that up, here's what we get, or just keep, not just pair that up, but we're moving in the zy plane, the zx plane, and all the planes in between. So what we wind up with is this paraboloid. It's just taking the xy, the parabola in the zx plane, the parabola in the zy plane, and just rotating them around 360 degrees to get this paraboloid. So let's find f sub, we're getting the volume here. The volume of a surface, or the volume under a surface, is defined as this. It's a double integral. We go a to b, c to f of x, and then we integrate the function f of xy. First, in this case, dx, or dy, dx, then dy. So how do we set this up? Let's move to the next blackboard to see how to do that. So we're finding the volume under this function over the square in the xy plane with these vertices. So let's see what that square looks like in the xy plane. Those vertices are here, 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 and here. And when we draw the square, we get this square. So clearly there are 4 regions, and so what we're going to do is take 4 times the area over this region right here. But we have to define that region in a very specific way to do a volume integral of this type. And so let's see how we do that. So here's the enlargement of that. And we've got the points 0, 1 and 1, 0 labeled. Now to traverse this region, we have to traverse it in 2 ways. First, we're going to take a slice, representative slice this way. You'll remember that from Calc 1 as the way we did integrals. Let's note what this x-coordinate is by noting that this function right here is y equals 1 minus x, which is the same as x equals 1 minus y. So this x value right here is 1 minus y, and this x value on the other end of our slice is 0. So we're going between that point and that point, and taking all of these representative slices that would have this is their right hand x value, and this is their left hand x value. And then what we're doing after we do that integration is we're going to traverse the region from here to here, from 0 to 1. So here's what our integral looks like when we set it up that way. So we're first integrating with respect to x, and by plugging in these limits, we're then going to put everything in terms of y, and then we can integrate dy. So let's do the dx integration first, and that gives us this part right here does not change, and we get x minus x cubed over 3 minus xy squared, evaluate between 0 and 1 minus y, and then we're going to integrate that dx between, or dy between the limit 0 and 1. So if we plug in 1 minus y and 0, here's what we get. So we're going to be able to integrate this term and this term as is, but here we want to multiply out to get minus y squared and plus y cubed. So integrating term-wise, we integrate the 1 and get y. We integrate the y, minus y, and get minus y squared over 2. We integrate this term, and we can do it as a group. It becomes 1 minus y raised to the 4th power over 12. If you differentiate that back, you'll see that you get this back, and then we integrate minus y squared and get minus y cubed over 3, and y cubed finally, and get y to the 4th over 4, and everything is evaluated between 0 and 1. So let's copy all this over onto the next blackboard. When we plug in the 1 and the 0, all of the terms except 1 are going to be 0 at 0. So this term, this term, this term, and this term are going to equal 0 when we plug in 0, whereas this term right here has actually equals 0 at y equals 1, and then we have to calculate it at y equals 0. So let's go through those calculations, and note that for this one here, that's when we plug in 0, so it's the negative of this at 0. And then if we get a common denominator of 12, we see that we get this, right? 12 from the 1, 6 from the half, 1 from the 1/12, 4 from the 1/3, and 3 from the 1/4. And if we combine all those together, we get 4 times 4/12, which is 4/3. And remember, we were multiplying by 4 because way back we were just calculating over this little region right here, and there were 4 of those regions. So we're going to wrap up this video now and have one more video on this chapter of functions of several variables, and possibly have one later video working example problems, but this is the last video coming after this one that's got theory and examples in it.